Okay, I'm going to talk about simple harmonic motion, and the model that I'm going to use to talk about it is this right here. I've got a dynamics cart with two masses on it and a little flag to help the motion sensor over here see the cart. The cart is connected to two springs that are right here, and both of them are stretched out so that the cart is just resting right there in equilibrium, meaning both of the springs are pulling it equally in either direction. This spring is hooked up to a force sensor over here, which measures the tension in the spring, and that force sensor is reading out on the screen right now. So you can see the force is about almost zero. So let's just think for a minute, how would I increase the force on the force sensor? Well, it's at a minimum now. If I move the cart in either direction, the force will increase. Okay, I'm back to equilibrium, and you can see the force is pretty close to zero. If I move over here, same thing. The force goes up the farther away I am from equilibrium. So the hallmark of simple harmonic motion is that the restoring force obeys Hooke's law, meaning that the restoring force, pushing it back to equilibrium position, is proportional to how far away from equilibrium it is. The farther away, the bigger the force. The closer, the smaller. As long as the restoring force obeys Hooke's law, the motion will be simple harmonic motion. So let's take a look at what happens when I push this cart away from equilibrium and let go. Okay. The cart is going to go back and forth in simple harmonic motion. So now, because we have it hooked up to this force sensor and motion detector, we can record the position and force as it moves back and forth. And I'm going to do that now. I'll give it another little push here, then I'm going to come over and press record on Logger Pro. And you can see the blue line represents the position of the object, the red line represents the force, and you can see that they're tracking each other pretty perfectly. Okay, so because of that, we could say that the force is directly proportional to displacement from equilibrium, and that is what makes simple harmonic motion in general. So let's just think a little bit more deeply about this system and the implications of it. So the first question I want you to think about is, what feature of that graph would tell you the velocity of the cart? Okay, check your neighbor. What feature of that graph would tell you the velocity of the cart? Okay. If you said that the slope of the position versus time graph would tell you the velocity, you're right. That's a good job. So in order to kind of see that, we can actually pull up here another data point for velocity, and now it will show up in green. Okay, and interestingly, it looks like the velocity graph is shifted over. So what does that tell us about the motion? When will the cart be going the fastest? Will it be going the fastest when it's far out here away from equilibrium, or will it be going the fastest when it crosses back through equilibrium? And to try to see in a little more detail what will actually happen, let's zoom in on just one of the back and forth motions. Okay, so here we go. It looks a little bit like the path of snakes squiggling through the sand. So now let's see. Here we are at zero position, essentially, and that's when the velocity looks like it's at a maximum. Okay, so we need to try to make sense of that. And then the next question is, when is the acceleration maximum? Okay, so As you're thinking about that, remember what Newton's second law says. It says the net force equals mass times acceleration. So, all right, check your neighbor. At which place in the motion will the acceleration be the greatest? All right. So the question is this acceleration the greatest here in the center at equilibrium? Is it the greatest somewhere out here when it's at its maximum amplitude? Or is it at the greatest over here at its maximum amplitude on this side? Or is it somewhere else in between? Or can you not tell?